Log on, tune in, find out. Another good idea from Cambridge.
Thank you very much to all the organizers for inviting me here to this nice institute. It's a pleasure to give this talk here. Okay, I will speak loud. So what I would like to present is how free-discontinuity method may apply to inverse problems. Free-discontinuity method comes from calculus of variation, from my point of view, which is more theoretical, but essentially comes from many imaging applications, and they might help us also in treating inverse problems. And the idea is when this might be of help. Well, this happens when inverse problems have unknowns which are characterized by discontinuous functions, and especially when the discontinuity of these functions carries important information. And I got here a list of cases in which this occurs, and essentially I'm going through quickly the first two cases, which are more natural, and then I'm going to focus my talk mainly on the third one, which is maybe less intuitive. So the first case is clearly when you have to recover some discontinuous coefficient, and for instance you may think this on the inverse conductivity problem or Calderon problem, as you wish, when you have to determine discontinuous conductivities by boundary measurements. The second case is when you have to identify shapes, and I'm thinking here of domains or open sets. And here the discontinuous function comes into play if you look at so you characterize shapes in terms of functions by using characteristic functions, and clearly the discontinuities of the characteristic functions are actually a boundary of the domains. So you can have this way of seeing these things, and this happens for instance in obstacles or cavities determination. Then I'm presenting briefly an example in this industrial application, which is called photolithography. And the third case is rather less intuitive, as I said, and it's when the discontinuous function is actually not in the unknown, but is part of the solutions of a forward problem are discontinuous, and where discontinuities may carry important information, and this is the case of, for instance, crack problems. Okay, so I'm just going briefly to advertise some of the work that's been done in this area by showing something that's been done in the electrical impedance tomography in the case of discontinuous conductivities. And I have two examples why this might be important. Okay, this one is exactly what Matti Lassas did more or less yesterday. So you have a domain discretization, so you subdivide your domain omega into given subdomains, and you assume that your conductivity is constant on each of these, so it is piecewise constant, and what is to be determined are these unknown constants k, a, I. So okay, the uniqueness results are due to Isakov for any dimension, and then this of course fits into the Astala-Paivarinta general results for n equal 2. We have a very nice results by Alessandrini and Vasella saying that this problem is Lipschitz stable. What inverse problems teach you is that you may not be too greedy. You cannot have a very fine discretization because this Lipschitz constant is exploding exponentially with a number of subdomains. This is the bad news. But this n is fixed, yeah, n is fixed. And then, of course, this is clearly useful for imaging, medical imaging application is the inverse inclusion problem, when you have some inclusion with different conductivity, and you might think that the conductivity of a background and maybe also the inclusions is known, and so we want to determine shape and location of these sets. And again, you have stability of logarithmic type due to Alessandrini and Di Cristo, which is optimal because also this problem is severely ill-posed. Okay, and what you do when you have to deal with discontinuous conductivities, well, you try to, of course, the problem is ill-posed, so you need some kind of regularization, and usually you use some kind of natural regularization. One example is, of course, the total variation regularization, and this has been used by Dobson and Santosa in connection with a discretization method for the computational purposes, and by Tony Chan and collaborators with level set methods. Another option, which comes directly from free discontinuity methods, is to use the Mumford-Shah functional, which has been proposed for segmentation in imaging in the late 80s, I think. And the Mumford-Shah functional, here you have simply the n-1 dimensional Hausdorff measure, and this J or sigma is the jump set or discontinuity set of your function. And this has been used in collaboration with Santosa with a phase field function method for computational purposes. And let us just have a look in these examples how these two things read. And well, essentially in the domain discretization, the total variation is exactly, this is a formula that Lass has used yesterday again. So if you have two adjacent subdomains and you measure them where the intersection of their boundaries, then you are measuring how the two constants are different. And if you use the inverse inclusion problem, then this goes down in both cases essentially to a perimeter penalization, maybe weighted or not, but essentially this is a perimeter penalization, which is very common in this field. What is more important maybe is that the use of this kind of regularization has been justified rigorously, and this has been by gamma convergence, by a variational analysis essentially based on gamma convergence. So what does this mean, justified? It means that if error on your measurement goes to 0 and you have a suitable choice of a regularization parameter, then the minimizers of your problem are going to converge to the looked for solution, to the looked for conductivity, to the non-conductivity. Okay. So the second case, I'm going to show an example taken from this industrial application, which is, oops, I don't want to break this one. And this is a joint work with Fadil Santosa. And what is the problem here? Well, essentially, you have the photolithography problem is a process which helps us build and integrate these circuits, and it works in the following way. So you have light coming from above, it passes through a mask, the mask simply lets the light go through or not, then it goes through some lenses, some optics, and it reaches here a photosensible material. And this photosensible material is done in such a way that if a light intensity is above a certain threshold, then it can be developed and it can be washed away. And then use this dent here to etch the next layer. Then you remove the photosensible material completely and use this as a print for your circuit. So the main question here in this problem is, so I would like this to be exactly equal to the desired circuit, and what is going to be the mask I should put here, because of course, since you have diffraction and diffusion effects due to the optics, well, the mask and this circuit are going to be different, of course. And well, maybe you may not be able to reconstruct the exact circuit you would like, but maybe you would like to construct the best possible with a suitable choice of a mask. And the mask model is simply the following. You think of a mask of being a domain, a set, an open set, and you modulate by taking its characteristic function, and the light intensity is given by this kind of functional, which contains two of two kernels. The kernel K is the so-called coherent point spread function, and the kernel K, which is the mutual intensity function, models the so-called partial coherence of life. So to just understand what's happening here, if you have full coherence corresponding to J equivalent equal to 1, then your intensity function is just the square of this convolution with the coherent point spread function K. Okay, so this is a kind of double convolution. It's very smoothing, so your mask is going to be blurred in the intensity, and this is the intensity of light at the photosensible where the photosensible material is posed. Okay. So what is the idea? Well, the idea, you have this intensity. The threshold, depending on the material, is given by this h, and then you take the region where the intensity is beyond this h, and you can read also in terms of its characteristic function of this set omega of u, and this is simply the Heaviside function applied to the intensities minus h. And then the idea is, if you have a mask, when what you are really able to construct is this circuit, which is omega d, which is omega of the characteristic function of a mask. And the idea is, well, I would like this to be as close as possible to the desired circuit. Okay, so this is the desired circuit I want to reconstruct, and I would like that this omega of d to be equal to omega naught, which might not be possible to achieve, and so you can put this in an optimization setting. And so you take a class of admissible mask. It's convenient to take a larger class rather than open sets, and you take sets of finite perimeter, and then you set this as a minimization problem with respect to a distance. And with Fadil Santosa, we investigated mainly these two issues by now. So what is going to be the distance between two circuits? And we chose a BV related distance, which might be useful also for matching and evaluating the distance between shapes in our inverse problems. And then we develop a regularization and computational approach, and here is where free discontinuity method comes in. And because we consider a quite natural perimeter penalization on the mask, we employed phase field functions to have a easier computational method, and also instead of taking the Heaviside, which is highly nonlinear and it is discontinuous, we smoothed it out with a smooth version of it, which simplified the computation a little bit. Okay. And this is just to advertise some of the work has been done in this area, and you can try to import into your favorite medical imaging application. And now I'm going to the main part of the talk. I would like to talk about this inverse crack or cavity problem, where the discontinuous function to be recovered is the solution to the forward problem. So what is this problem here? So you have a usual problem of the following kind. You have a conducting body. In this conducting body, you have some defects. Mainly here, there are lots of structure here, but just focus on these two parts. This is a crack, okay? You can think this in any dimension, but it's easier to figure it out what is in 2 dimensions. So let's think just that the defect may be a crack or might be a cavity. And this is characterized by this set K. K, in the case of a cavity, is only the boundary of the cavity. Okay, and the idea is you would like to determine these kind of defects by performing electrostatic measurements at the boundary, the usual current and voltage type of measurements. So what you are assuming here that there is a region omega 1, which is free from defects, and there is a part of its boundary which you can access and you can perform measurements there. So essentially we are going to prescribe a current density here on gamma 1. This induces electrostatic potential, and which we are going to measure on this gamma. So don't worry about this complicated geometry. Just think that gamma is equal gamma 1, and since just think what we are trying to recover interior defects, and just think that gamma is equal gamma 1 is equal to the boundary of omega. So don't worry about all this other structure. And I'm denoting by GK the domain which you can reach from this part where you have measurements without crossing K. So essentially it's omega minus K and minus these gray parts which are the other connected components. Okay. So the forward problem is the following. I'm assuming that the defect is perfectly insulating, and I'm prescribing a current density F with some compatibility condition which is supported in gamma 1, and then this gives rise to an electrostatic potential in omega, which is the solution to the following Neumann type boundary value problem. So it's harmonic outside the defects, in omega outside the defects, satisfies this no flux condition across K, across the defect, which means that you don't have current going through the defects, so the defects are insulating, satisfy the prescribed current densities on gamma 1, plus these are simply normalization conditions that ensure uniqueness of your solution, but really are not very important. And of course the potential depends clearly on the density you apply, but mostly depends on the geometry, which is given by omega minus K, so it depends on K. And the inverse problem is the following. If UK is unknown, and then what you do, you prescribe a current density on gamma 1, then you have this electrostatic potential, and you measure it on gamma, and we call this measurement G. So F is a Neumann datum, G is the Dirichlet datum, and we measure it on gamma. So we measure the current and the voltage. And the idea is if we can recover from one or more of these measurements information about shape and location of possible present or possibly present defects K. And what does it mean, more measurements? Well, you can take you can change your prescribed current density and do the same experiments, and you have another couple of Dirichlet and Neumann datum, and so you may have 1, 2, 3, or possibly all measurements, but I'm mainly interested in having few measurements and not the whole Dirichlet to Neumann, Neumann to Dirichlet map, essentially, in this kind of problem. Okay, about this inverse problem, there has been a lot of work, in particular also about stability and reconstruction method. I just want to list a few contributions for the case of uniqueness, for the issue of uniqueness. This problem essentially started by the paper by Friedman and Vogelius, and what I want to address is here only the following fact, that in 2 dimensions the situation is pretty clear. 2 measurements are good to identify a lot of these kind of defects. It's a very general situation, it's very well understood, and still in 3D for crack problems this is still an open. I think Alessandrini gave a lecture a few weeks ago on this problem here, but essentially we still don't know for insulating cracks if finite number of measurements is fine. And we know only that the 2 measurements are good only if the cracks are plane. So this is still pretty much open, I would say. Okay, but I'm focusing in this talk about reconstruction. And the idea of reconstruction is the following. I would like to use a 2-steps procedure. So what I have here is my Cauchy data. This is prescribed, this is measured, this is the Neumann datum, this is the Dirichlet datum. And I would like to use a continuation procedure and get from the Cauchy data the electrostatic potential U all over omega. Then, when I have that, when I would like to recover the some features of a defect. Okay, let's look at the step 2 here, which is maybe somehow easier. So what you do? Well, this is usually from a theoretical or practical point of view. What you usually do, you exploit some features of your of the solution of your forward problem to identify some properties of your unknown. In particular, you use level sets, critical points, singularities, and so on. In this particular case, if you have an insulating defect, well, you take the jump set of U, and the jump set of U is a subset of K. Okay, let's think that this is just K. Okay, in particular, what is the idea here? The idea is, since this defect is insulating, what is happening to the potential is that usually it's jumping across the defect, and so you want to exploit that. Okay, so you have this idea. So what is the idea? If I'm able to, from a Cauchy data, I'm able to find the electrostatic potential of U, I might be able to compute this jump set, and I find a part of a defect. There might be some part of cracks which are invisible to a certain measurement, so you change the measurement, and you hope to find another portion, and you patch up the whole thing, and if you have a uniqueness result, in principle, you should be able to do that. So the problem here actually is, well, going from here to here. And this is I'm going to explain a little bit how to do that by variational method, essentially. So what is the idea? So this continuation problem going from a Cauchy data to U is a rather nasty one, because, well, of course, continuation is ill-posed, okay, that's okay, part of a problem, but also you have a not classical continuation problem, because U is harmonic in some domain which you don't know. So you have a continuation problem in an unknown domain, and this is very difficult to solve, and so this is where free discontinuity methods may help. So the idea is the following: rather than look at this as a continuation problem, I would prefer to state it as a free discontinuity problem. And the idea is the following: I have a Cauchy data GF, and I look for the potential, which is a discontinuous function, and I don't know where its jump set is. I would really like to know where this jump set is, and if I take this as the closure of this jump set, then I hope to find this discontinuous function solving the following problem. So it's harmonic outside the jump sets. It has a homogeneous Neumann condition on the jump set, and it satisfies this overdetermined condition on the boundary. So you have overdeterminacy of a boundary, but K is essentially an unknown, so this compensates the two things. And so I would like to solve this problem, and the important fact is that the discontinuity set is unknown, and this is where free discontinuity comes in. And of course, before just attempting to do that, well, you need to prove that for Cauchy data G and F, this continuation is unique, at least if you have compatible Cauchy data, and this uniqueness is proved early in this project in 2006. So you might have some hope to recover this. Okay, just few words about some notation of the problem. So I assume that K naught to be the known defect. I'm considering two cases. The first case is K naught is a crack, so K naught is the union of a finite number of cracks. Everything I'm telling here works in any dimension, but think in two dimensions with a finite number of curves. Or or K naught may be a cavity, and the cavity is the union of a finite number of open sets, and here K naught denotes their boundaries, okay, only. So I prescribe a current density F naught, U naught is the exact potential, and G naught is its measurement. So the unknowns here are K naught and this harmonic function U naught. In principle, you should be able to have the Cauchy data exact, but actually this is not possible because these are measured, And so what really is available are noisy Cauchy data, which are G epsilon and F epsilon, where epsilon is simply the noise level. And you can't forget about that because the problem is ill-posed, severely ill-posed, and so you need to take into account the noise here. So I need some hypotheses on the defect, which are very simple. I need some kind of C1 or C1 alpha regularity. And this main assumption is the following. I need to find a Q which is strictly greater than 2, such that the solutions to the forward problem with this defect K naught satisfies this higher integrability condition. And this is not really a restricted condition, it's a geometric only condition, and it comes out essentially from the higher integrability in the interior for elliptic equation due to Meyers, which has been extended up to the boundary in some cases by Galois and Monnier. So this is not really a restricted condition, and it applies to most of your favorite crack or other kind of structure situation. But I need this Q here, even if, well, it will not be very clear why, but in any case. Okay, so I'm setting the problem in the usual least square formulation. So I have a noisy Cauchy data. I would like to reconstruct U naught, and I take K in a suitable class of defects, and I try to match here the Dirichlet datum here. And of course, the Neumann datum is coming into the solution to the forward problem here. Clearly, there are, if you want to solve this problem, you have some things to take into account. And the main difficulty here is the following. You have to minimize oversets, and this is not always an easy task from a numerical point of view. And so one possible solution is to use phase field function. I'm going to explain in a minute what that means. There are others, of course, but this is one possibility. And the other is the instability. And you need to regularize this process. And the idea is to use one kind of minimal kind of regularization, which is to use length penalization. So essentially, you penalize the length of a defect here, okay, plus this other term, which I'm going to explain exactly now. So what is the idea? Let's look what this means in the case of crack. So in the crack case, actually, instead of having here the measure of K, you have a measure of a jump set of a solution. And what is this here? Well, this is actually a kind of Manford-Shah regularization on the solution of the forward problem, on the potential. Okay, so this is where free discontinuity is appearing here. And the only difference is that you are taking here P, which might be possibly greater than 2. But this is a Manford-Shah-like regularization. In the case of cavities, I'm keeping this term just for symmetry with the previous one, but essentially this goes down to a more common perimeter penalization on the cavity, essentially. Okay, what is the phase field approach I'm going to consider? Well, the idea is very simple. You take a crack and you enlarge it to thin delta neighborhood, and then you consider the problem, instead of having here a crack, you consider a thin cavity. And you may reread this in the following way. If you have a thin cavity, you might think that the conductivity outside the cavity is 1 and inside the cavity is 0. So you can think that this formally may be rewritten in the following way, with here the cavity is encoded in this conductivity here. And then what you do, this is the same problem as before, well, you replace this discontinuous and binary function with a smooth version of it. You take a smooth function between 0 and 1, and essentially you have that the conductivity here is going to be 1 outside the cavity, going smoothly to 0 near the boundary of the cavity, and stays 0 inside the cavity, the thin cavity, and you take this coefficient here, you call V. This is a smooth phase field function, and this V epsilon is simply a rescaling because I want this function to be close to 0 near the cavity, but not exactly 0, so not to have a degenerate problem. But it is simply a rescaling. Don't need to worry about that. Okay, so given a phase field function, the potential, I can define the corresponding potential, and I can solve this problem. And I would like to find a phase field function which is matching my Dirichlet datum as best as possible, plus some regularization. What are the advantages here? Well, first of all, you minimize over smooth functions and not over sets anymore. And then also the forward problem, the geometry disappears, because you have only the change in the coefficient, but the geometry is given fixed, is omega. Okay, the problem is which kind of regularization we should put here, and we propose the following method. So this is the function we would like to minimize. So this is simply the fidelity term plus some coefficient here, which is essentially the regularization parameter. And then this is the regularization. Okay, what is this regularization? Well, this is nothing I came up, it's not out of my mind, because this is the Ambrosian-Tortorelli functional, which is the phase field approximation of the Mumford-Shaw. So we are actually using simply the corresponding approximation for phase field function, which is the pretty much analogous of Mumford-Shaw. So what is the idea? The most important term here maybe is this one, which is V, which is a single well potential centered at 1. And the idea is the following. So this makes your phase field function like to be at 1. So the phase field function is going to be at 1 in a large area of your set, but it might go to 0 somewhere, and where it should go to 0. When V goes to 0, this is very small. So this might be very large. So the gradient U might be very large. This means that U essentially might jump where V is small. So the idea is when U jumps, you make V small to allow this not to be too big, and everywhere else you take V equal to 1. Okay, so V encodes, indeed it's encoded where V is small, you have the jump sets of U. So this is also a way of finding easily the jump sets. Okay. The idea is we would like to justify this kind of regularization by a kind of convergence result. So in some sense we would like that minimizers of this allows us to produce some function which converge to the exact U0, to the exact potential. But unfortunately, even if we have some options here, well, unfortunately we don't have a convergence result, and I think that you cannot have a convergence result for this particular problem, but there is a strictly related problem when you choose P equal to Q when we do have a convergence result. But this strictly related problem is more complicated, much more difficult to implement, and so I think that this still is a good model to work with from the point of view of the application. And also, if you look at this reduced model, when actually, it might be strange, but this is it, the coefficient here to be chosen should be actually equal to P equal to 2, which also simplify a little bit the numerics out of it. Okay, let's look briefly at the cavity case. So if you a priori know that you have a cavity to be determined, well, the only thing you need to do, you take the same function as before and you replace this the single well potential with a double well potential centered at 0 and 1. And what this means, it means that so what is the difference? Maybe I have okay. So what is the difference? So what the single well potential should do. So if you have a crack here, you have a jump in your solution, the phase field function you are aiming to reconstruct should look like this. Should be 1, then goes down to 0 near the crack, goes up again, goes stay to 1, goes down, and so on. If you have a cavity, what happens is that your phase field, you replace this with a double well, your phase field is happy either at the phase 0 or at the phase 1. And so if you have a cavity here, what your phase field should do is to be 1 outside the cavity, going smoothly down, close to 0, stay to 0 inside the cavity, and then goes up again. So these are the two differences. Okay, the cavity case actually is much simpler because we have a convergence result there. And so this is fully justified, the use of this, and this is also gives some justification to the other case to use this kind of functional also for a crack case. So think of this V epsilon just to be a minimizer of this functional, of the functional I showed you before, and this satisfies this condition. I need a technical assumption because working with BV is not easy, and well, I need some technical assumption on V epsilon, but then as the noise level goes to 0, if you have this V epsilon, you can construct this function here, and this function is giving you, is converging to U naught. So to the exact solution. So the solution to this are good approximation of this one. And also, if you threshold, I can go maybe B. So the idea is this method allows you to easily identify where the defects are, because you just threshold your phase field, and when the phase field is below a certain threshold, then this is where something is happening. So here is where the cavity is, and here is where the crack are. And so if you threshold this, then this is going to converge and to the exact cavity, and so you recover the cavity also in this case. Of course, you need this technical assumption, but in any case, this is justified by this convergence analysis. Okay, in the last 5 and something minutes, I would like to show some numerical results based on this approximation, this optimization problem, which have been done in collaboration with Wolfgang Ring from the University of Graz. So what is the idea here? I'm starting with a single well potential, so crack case, and I have, so here, okay, the white part is the crack to be reconstructed. What is depicted here is simply the final phase field, where the blue is 0 and the red is 1. And clearly you can show where something is happening here. So this is reconstruction with noise-free data, 6 measurements, or what I mean by these measurements. So the idea is the following. I have 4 electrodes, 1 on each side, and my measurement, I take the current density to be the following. I take 2 of these, and one I take it to be positive and the other to be negative. Okay, and then I inject this kind of current, and I measure the Dirichlet datum, the voltage, all over around. So I have these currents, east-west, okay, and or maybe west-east, south-north, and then current flowing from each of the 4 angles. So 6 measurements. Okay, I'm interested in having few measurements as possible. Okay, this is pretty robust with respect to the number of measurements. If you decrease it and you reduce it to 3 measurements, here we have 1% noise. 3 measurement means I don't have any more of the electrodes here on the south. I only have these 3 ones, and well, clearly the reconstruction is slightly worse, but still is pretty good. And this is, to have 3 measurements is interesting because these kind of measurements are the ones that at least in 2D guarantees you uniqueness. 3 measurements, so 3 electrodes is enough to have uniqueness for the crack problem, in 2D at least. And clearly what you are missing here is information of the current going exactly in this direction. This is probably the current that gives you more information because it's one that is eating mostly the crack, because the other current is going here and is going here, and they might miss essentially the crack, so they don't give very much information, and this is why maybe this is slightly tilted. Okay, this is also pretty robust with respect to noise, because, well, this is 1% noise, this is 5% noise, free measurement again, and you may notice that there is no need to give any a priori information on what the defect is. It might be 1 crack, 2 cracks, 3 cracks, 1 crack in cavity, whatever. You don't need any information a priori on the number of cracks. You don't need to set this up. But the method just gives it to you. Okay, then I think, okay, let's move to the cavity case. So this is I switch to the double well potential instead of a single well. So I'm looking for cavities now, and this is a reconstruction of 2 cavities with 1% noise and a single measurement. So I think it's this left-right measurement I have, and the reconstruction is pretty good. And of course you need to consider this is an exponentially ill-posed problem, so okay, the construction is what it is, but it gives you exactly the location at least and the number of parts, and then maybe you may use another method to this as a starting point for another method that maybe gives you a better location of this object. Okay, and also here we're interested in having a single measurement is because for cavities a single measurement is enough in any dimension. This is pretty well understood. So 1 measurement should be enough, and actually in some cases is enough. Okay, and I would like to conclude my talk by a comparison on how the method with a single well potential and the method with a double well potential work in the same kind of situation. So you have 3 measurements, 5% noise in these last 3 examples. So if you use a cavity method for detecting this cavity, well, okay, it works. What happens if you use a single well potential? So if you are looking for crack-like structure. In principle, this should work and should give you the boundary. Actually, it doesn't. So what is doing here? What is the problem here? The problem is that the problem is ill-posed. So the cavity and this kind of structure essentially have a very good match on the boundary data. So you cannot really distinguish them if you have some noise. And so what is coming into play here is that maybe the Manford-Shah is prevailing, and the Manford-Shah is trying to minimize the length, and so this is shorter than going around. It's trying to find a skeleton of it. And also, if someone is familiar with the Manford-Shah, this is a very nice tripole point, which is one of the structures that Manford-Shah likes to create. So this is how it works. So you may also wonder what happens if you want to recover a crack and use a cavity method. And actually this works almost as well. So if you use a cavity method to determine a crack, then you simply get a thin cavity around it, which is nice. And also you notice also the same kind of behavior you have here. So you have a crack with a sharp angle, and it's trying to smooth it down to lower the length and adding this extra path here just to get this singularity in some sense. So this is something that this method likes to do, but still the location is very well recovered. And finally, since he likes to build a structure like this, where we try to look what happens if you want to reconstruct something like this, which is a rather difficult crack to reconstruct. So you take a Y shape here, and you have the reconstruction with the crack method gives you a pretty good reconstruction with 5% noise, but also the cavity method, I think, gives you the main feature of this defect in here, and so this is not bad reconstruction at all. And so you can have a flavor of how this works in these examples. And I think with that I can stop here, and I thank you very much for your attention. Okay, actually this is, I don't know, the parameter tuning is very complicated in some sense. What you can really do, essentially you can have some freedom in, so you have this epsilon is a noise level parameter, and then you have some kind of parameter depending on the Manford-Shah, and you have some freedom to choose them corresponding to each other in some related way. You have some freedom to change a little bit because this parameter epsilon is showing how fast this is going down and up. Okay, you have some freedom to relate the noise level with this parameter, which is depending on the Manford-Shah. They need to be some functions relating one to each other. So you have some freedom in doing that. What is the exact parameter you should put here? Well, this is open to speculation.
What did you use?
I don't remember if I just used probably the same kind. But you know, if you use the synthetic data, you don't really know what the noise level is. And of course, this works in the asymptotic for fixed epsilon. You don't know. You might have other constant here, other tuning parameters, and yeah, I don't know exactly. You try, of course, to force as much as possible a good match here on the data, and but still sometimes the Manford-Shah factor comes into play.
Just a quick question on when you had two cracks with three measurements, and
Yeah.
you had 1% and 5% noise.
Yeah.
In both cases, the reconstruction looks quite similar. In one, it was bent and on the same side, and the other, it was straight and next to it. I just wondered if you tried different types of noise or different realizations of the same noise.
Okay.
It's always the same way.
It might be sensitive. I mean, independently of a noise level, if you do another random noise and you perform another experiment, you might obtain different solutions. Okay? And sometimes you obtain completely different solutions. So it might be dependent on the noise.
I think Gaussian noise.
Yeah.
Because I think it's important, especially in a nonlinear problem, to take lots of samples of the noise.
Yeah.
You might only put one on the slide, and it might be representative. But then the question.
Yeah, there are some other sometimes the method don't get one. For instance, let's go back to. It might happen in some examples you are missing one of them or something like that. It might happen even with the same level of noise. Okay, if you do another realization of a noise, it might change a lot. It might happen, yeah.
In your numerical examples, you're suggesting that if you use an algorithm using double potential, it's sort of program says, well, I'm looking for cavities.
Yeah.
And if you have a single layer, you're looking for cracks.
Yeah.
So in some sense, it's sort of an a priori knowledge that whether you're looking for one or the other. So I suggested, what happens if you sort of took your potentials to be a linear combination, in some sense? Would that?
This is something. It's an interesting problem, and it would be interesting to find a way of the method automatically choose which method to use. But essentially, with a single well potential, you get you are looking for curves, and for a double well you're looking for open sets. And in principle, the single well, if you have an open set, a cavity, you are looking for its boundary. So in principle, that method should work if you have any general kind of defect. But as we have seen, sometimes it's not going for a boundary, but for some other different realization. But in principle, that should work with any kind of defect you might imagine. And yeah, it would be interesting to have a way of choosing, maybe during the iteration, which one of the two to have. But this is, I don't know.
Quick question, quick comment. So if image analysis people and inverse problems people would like to talk to each other, use Luca as your translator since he speaks both languages.
Cool, so.
Yes.
Thank you very much.